Now, as an example, let's look at the Feynman path integral for a free particle. The definition, this was what we had derived for the path integral, where this measure is given as the product of the measures of each one, the positions of the particle at different times. This is the normalization, and the action is given by this sum in the discrete case. And in all our expressions, we will understand that we will be taking the limit n goes to infinity and epsilon goes to 0, such that n times epsilon is fixed. It's our time interval. Now let's write it, the path integral expression explicitly. Tf minus ti xi, this is equal to the product of dxt, let me just write it, dxn, n from 1 to n minus 1. Keep in mind that x0 is fixed to be xi and xn is fixed to be the final position. And then we have this constant to the power n over 2. And then we have the exponent of I, n from 0 to n minus 1 of m over 2 epsilon xn plus 1 minus xn squared. Now the way we will evaluate this integral is just evaluate these integrals one by one and try to see a pattern such that we can generalize to that pattern to an arbitrary n. Now let's start with n is equal to 1. Let's look at the x1 integral. Now the x1 integral, let me just write the terms that contain x1 only. In the exponent, I m over 2 epsilon. When n is equal to 0, here we have x1. And when n is equal to 1, here we have x1. So there are two terms that contain x1 in the sum. And let me write them out. x2 minus x1 squared plus x1 minus x0 squared. Now and x1 goes from minus infinity to plus infinity. Now we will just evaluate this using Gaussian integrals. Let me just simplify the exponent a bit. Exponent of I m over 2 epsilon. Well, here there is 2x1 squared, one coming from this term, the other one coming from this term. And then we have minus twice x1, the linear term is x0 plus x2. And then we have x2 squared plus x0 squared. So this is the cross terms from each one of these squares. And x2 squared is from this term, x0 squared is from this term. Now let me just rewrite it once more. Exponent of minus m over epsilon minus I m over epsilon x1 squared plus minus I m over 2 epsilon x0 plus x2 multiplied by x1 and plus I m over 2 epsilon x0 squared plus x2 squared. Now this integral I will evaluate just using the Gaussian integral minus alpha x squared plus beta x from minus infinity to infinity. This is just the square root of pi over alpha exponent of beta squared over 4 alpha. So my x1 integral just becomes minus infinity to infinity. Now I evaluate that integral. So there are terms that are independent of x1. So I have exponent I m over 2 epsilon x0 squared plus x2 squared. And then there is the square root of pi. Now alpha is the coefficient of minus x squared. So the minus x1 squared, the coefficient is minus I m over epsilon. Then there is the exponent. Beta squared, beta is the coefficient of x. So in this case the x1, the integration variable, the linear term. So we have minus I m over 2 epsilon x0 plus x2, all of this thing squared divided by 4. Alpha is again the coefficient of minus x1 squared, so minus I m over epsilon. Now let's try to simplify this a bit. Now here this under the square root we have I epsilon pi over m. Then we have two exponents, I m over 2 epsilon x0 squared plus x2 squared. Then here there is the minus I squared, that is minus 1. Minus 1 divided by minus I is just I. There m squared divided by m gives me m divided by, well, this is 2. Let me check if that factor 2 is correct. No, there is no factor 2 over here. You see there is a 2 over here, 2 over here, they cancel. So there is no 2. And then we have 1 over epsilon squared. Here there is an epsilon in the numerator, it goes to the numerator. So we have divided by 4 epsilon x0 plus x2 squared. Now let's simplify it even further. I epsilon pi over m, exponent I m over 4 epsilon is common. Inside what we have is here x0 squared plus x2 squared plus twice x0 x2. And let me also check one more term. So this is there is a minus 1 over here, from minus I squared is minus 1, and here there is a minus 1 divided by minus I is minus I, so this term is also minus. So these terms, this is minus, this is minus, this is minus, these are all minuses. Then we have plus from here. You see I took out the factor 4, here there is a 2, so they come with a factor, overall factor 2. So 2x0 squared plus 2x2 squared. Now this minus x0 squared cancels this 2, one of these 2, and it minus x2 squared also cancels one of the 2. And we end up having square root of I pi epsilon over m, exponent of I m over 4. Let me just write 2 for the time being. Two epsilon of x0 minus x2 squared times 1 over 2. So this is the result of our x1 integral. I m over 2 epsilon x2 minus x1 squared plus x1 minus x0 squared. Now, one can see that this term, the result of this x1 integral, is actually very similar to just one of these terms over here. The main difference is that instead of, we have this additional factor 1 over 2. Now, let's evaluate the x2 integral. So we have the x2, the x1, from minus infinity to infinity, both of them from minus infinity to infinity, of the exponent I m over 2 epsilon is the common in all the terms. You see, let's just write all the terms that contain x2 and x1. So there is x3 minus x2 squared plus x2 minus x1 squared plus x1 minus x0 squared. So basically in the exponent we have this additional term that contains this x2. Now we had already evaluated the x1 integral. So this is equal to minus infinity to infinity dx2 exponent I m over 2 epsilon. Here we have x3 minus x2 squared. This term doesn't appear in the x1 integral because it doesn't depend on x1. And then we have these remaining terms, the result that contain x1. The result of the x1 integral is just we had evaluated. and it is basically x0 minus x2 squared with 1 over 2. Well, instead of that 2, let me just write k. And there's a I pi epsilon over m factor. Now we will see why we have this k over here in a moment. And of course in this integral, k is actually, this should be evaluated when k is actually equal to 2. Now again we can calculate this integral by converting it to a Gaussian integral and using the Gaussian integral result. So this will be equal to, let me first simplify the exponent, the x2 exponent of I m over 2 epsilon. There is an x2 squared, one coming from this term, another one coming from this term, so that will bring a 1 plus 1 over k. Then there is the, let's say with a minus sign, minus 2x2. Well, there is an x3 from here. And then from here there is an x0 over k. And then plus there is the x3 squared here and x0 squared over k over there from this term. And all of this thing is multiplied by square root of I pi epsilon over m. So let me just rewrite it a bit, simplifying a bit more from minus infinity to infinity, dx2 exponent of minus x2 squared. The coefficient of minus x2 squared is minus I m over 2 epsilon, 1 plus 1 over k. Then plus x2. Now the coefficient of x2 is minus I m over epsilon, x3 plus x0 over k. And plus these terms that don't depend on x2. Now we can evaluate the x2 integral. This will become square root of I pi epsilon over m exponent well, let me see, minus here this term has a coefficient. They are also multiplied by I m over 2 epsilon. Exponent of I m over 2 epsilon, x3 squared plus x0 squared over k. Now the result of this x1 integral is a square root of pi over the coefficient of minus x2 squared, which is minus I m over 2 epsilon, and this is a k plus 1 over k. And then we have another exponent of the coefficient of the linear term of the integration variable x2 squared minus I m over epsilon, x3 plus x0 over k, all of this thing squared divided by 4 coefficient of minus x2 squared minus I m over 2 epsilon, k plus 1 over k. Now let's simplify it further. We have square root of I pi epsilon over m and then from this term we have k over k plus 1 and let me write factor 2 over here. And here let me write a square root of 1 over 1 plus 1. So this basically, here we have a 1 over square root 2, here we have a 2. Now the reason why I wrote it in this form is such that this looks like this term over here, but for k is equal to 1. Now in x2 integral we have k is equal to 2. And then let's see, we have the exponents let's see, I m over 2 epsilon x3 squared plus x0 squared over 4. This is this term over here. Then let me simplify this a bit. We have the minus I squared, that is minus 1. Minus 1 divided by minus I is minus I, just minus I. And then we have m squared divided by m is m. Over here we have there is 1 over epsilon squared. This just goes to the numerator, so we have epsilon. Here we have 4 cancels, this 2 cancels one of factors 2 here. There is a 2 left, so I m over 2 epsilon. And then we have a k over k plus 1. x3 plus x0 over k squared. This is the exponent. Now we will need to simplify this exponent even further. So let's write this is equal to square root of I 2 pi epsilon over m, square root of 1 over 1 plus 1, square root of k over k plus 1, exponent I m over 2 epsilon. Let me also take out this k over k plus 1 out. So inside what is left is k plus 1 over k, or 1 plus 1 over k. This is k. x3 squared plus x0 squared over k. And then we have from this term there's a minus sign, minus x3 squared plus x0 squared over k squared plus twice x0 x3. This is equal to square root of I 2 pi epsilon over m. By the way, there are 2 factors of these. You see here there is another factor. So here this is 2 to the power 2. Then here we have n from 1 to 2, or 1 to k. And 1 to 2, in this case it is k. K will be just 2. Square root of n over n plus 1. Exponent I m over 2 epsilon k over k plus 1. Now let me open this parentheses. So I have 1 times x3 squared, that will cancel this x3 squared. So what is left is 1 over k x3 squared. Now let's look at the x0 squared terms. Here I have x0 squared, 1 times x0 squared over k, it will remain. Then I have this term multiplied by this term will give me plus x0 squared over k squared. But here I have a minus x0 squared over k squared, so they will also cancel. And then I will have this term over here, which is, here, by the way, I forgot a factor k over there. Then I have a minus twice x0 x3 over k. Well, let's see, each one of these terms have a factor of 1 over k, so they will cancel this one. So the final result will be 2 pi I epsilon over m, n from 1 to 2, square root of n over n plus 1, exponent of I m over 2 epsilon, x3 minus x0 squared times 1 over k plus 1. Now you see the pattern. Now here there is a factor 2. Now we evaluated x1 and x2 integrals. Each integral brings down such a factor. Each integral brings such a factor with n goes, initially n was 1, then it was 2 in the x2 integral. And here, if we said the result of the x1 integral was 1 over k, the result of the x2 integral is 1 over k plus 1. So basically, in this case, this is just 2. Now we can see the pattern. And if we, for example, evaluated the x3 integral, now this is 3, k is 2, so this is 3. So what the result will be, we will have another factor of this square root. And here we will get another factor, this time another factor like n over n plus 1, but this time for n we will have 3 instead of 2. So there will be 3 terms. And then we will get the exponent. This is all the same, x3 minus x0 squared, but the 3 will go up by 1, so we will get 4, etc. So now we can write the result of all these dxn n from 1 to n minus 1 of our integral. This will be equal to 2 pi I epsilon over m square root. You see, every integral brings such a square root, so here we have n minus 1 of them. So there's n minus 1. And from 1 to this time up, the last integral is n minus 1, square root of n over n plus 1. And we have the exponent of I m. Well, by the way, this is not x3, this is x4. We are already evaluating the x3 integral. So essentially, it's the next term in this x1, x2, x3, etc. I m over 2 epsilon. Well, the last one we evaluate is xn minus 1. So this is x4 becomes xn minus x0 squared. And here we have 1 over n. Now let's write these terms. Yes, let's look at this product first. So if we write it explicitly, 1 to n minus 1, square root of n over n plus 1, this is actually the product n from 1 to n minus 1 of square root of n divided by n from 1 to n minus 1 square root of n plus 1. So this will be under the square root. We have 1 times 2 times, well, essentially n minus 1 factorial divided by, well, this one starts from 2, but we can just add 1 and goes up to the last term is n, so square root of n factorial. So this is 1 over square root of n. So this integral n from 1 to n minus 1 dxn of the exponent of is is actually equal to 2 pi I epsilon over m to the power n minus 1 over 2. Now this product is just 1 over square root of n. And now we have the exponent I m. Now xn is just our final position, and x0 is the initial position. So, well, n times epsilon is our total time interval, and this is squared. Now the path integral is it has an overall normalization factor. Let's just check the normalization factor. So we have this term in addition to our integrals. Times 2 pi I epsilon over m to the power n over 2 minus 1 over 2, 1 over square root of n, and the remaining exponent, 1 over 2 I times 1 over 2 m xf squared minus xi squared divided by tf minus ti. Now note that this term over here in parentheses is the inverse of this term in parentheses. So this term cancels this n over 2 over there, and we will be left with m over 2 pi I epsilon times n under the square root, exponent of I 1 over 2 m xf squared minus xi squared, no, xf minus xi, all of it squared. Divided by tf minus ti. And again, remember, epsilon n is just tf minus ti. So this matrix element is actually given by square root of m over 2 pi I tf minus ti, exponent of I 1 over 2 m xf minus xi squared divided by tf minus ti. Now let's just do one consistency check of our result. You see, if tf goes to ti, we are left with on the left hand side xf xi, which should be Kronecker delta xf minus xi. So if we integrate over xf, this xf e to the power minus I h tf minus ti xi, and then if we take the limit as tf goes to ti, this should be 1. Let's see if it works. So this is our expression. I need to evaluate with respect to xf. Integral of m over 2 pi I tf minus ti, exponent of I 1 over 2 m xf minus xi squared divided by tf minus ti over xf from minus infinity to infinity. Let me just make a simple change of variable. Let me call x as xf minus xi. So my integral just becomes from minus infinity to infinity square root of m over 2 pi I tf minus ti, exponent of minus x squared minus I m over 2 tf minus ti. And this is just a simple Gaussian integral. With the result of square root of pi over the coefficient of minus x squared, which is minus I m over 2 tf minus ti. So let's see, this tf minus ti is cancelled by this one. I times minus I gives 1. This m is cancelled by this m. This pi is cancelled by this pi over here. And this 2 is cancelled by this 2, so it's solved without even taking the limit. Tf goes to ti, the result is just 1. So the normalization and the factors are correct.